Hello, my name is Rob Sides. I'm one of the product managers here at Amatech with responsibility for the single-channel and multi-channel line of Potentiostats. This includes instrumentation from both the Princeton Applied Research and Solutron analytical brands. So today's conversation topic is going to be on Electrochemical Impedance Spectroscopy, or EIS. EIS is a technique, and we're going to introduce this here as part of this introduction series with other chapters of electrochemical theory and potentiostat working theory. We'll touch a little bit on the applications, but you'll see the technique of EIS being discussed more thoroughly in the application series to follow. So the first thing I want to do is compare DC techniques and AC techniques, and this is going to be a little bit of a review from the previous introduction chapters, but also lay the groundwork for some of the different terminology that you'll hear through the course of this particular conversation. So we discussed previously when an electrode is introduced to an electrolyte, it's going to form an open circuit potential, and so this is just the potential that develops between that interface. At that interface, no net current is flowing. What we mean by that is electrochemical reactions are happening, but there's no net current flow to be measured. Only thermodynamic information is available. So at that point in time, we have not done anything. We've not applied any signal yet. So what I'm going to do with the potentiostat allows me to do is to shift the potential and thus causing electrochemical reactions to flow, and us to measure the rate at which those electrons move. So we're going to drive the potential of that cell away from its open circuit value to encourage or to dictate that electrochemical reaction happens. We can do that with different signal types. We can do that in the time domain or the DC signal types such as ramps and constant bias. But there's another way we can apply signals. We can do those based on AC waves or sine waves, and those we refer to as the frequency domain. So let's compare these. In a DC experiment, we're going to apply a potential that may irreversibly change the system because it may be a large potential. And the current is measured back is a sum of the current from all the different processes in the reaction. So if we contrast that to the AC experiments where we're going to apply a small AC wave of changing frequency. So an AC wave would be defined by its frequency and magnitude, and these experiments will typically use a fixed magnitude and a changing frequency. The frequency dependence of different processes and the fact that I am changing that frequency, I'm using that as my tool to probe different electrochemical processes and thus separate their contributions to from the total response. So the EIS fundamentals really want to take everything back to some of the primary equations and primary concepts we talked about in the introduction to electrochemical theory, and that was Ohm's law. And so Ohm's law really defines the relationship between voltage and current, that the ratio of those being the resistance. Now for AC methods, we're going to just turn that resistance value into the more generic term of impedance. It's more generic because this can cover impedance of any reason why current is not flowing in the cell. This could be resistance, it could be capacitance, it could be inductance, and it could be diffusion. We're going to talk a little bit about each one of those in the following slides. But the relationship is similar. It still defines the relationship between voltage and current. So here we're going to look at the AC stimulus applied as the voltage, and then the AC current measured as the response. And you'll see here pictured is the black AC wave is the potential, and the red AC response is the current. AC wave in, AC wave out. But the ratio in magnitudes of those two waves is going to determine its impedance level. So when we talk about the magnitude of impedance or its impedance level, that's one of the ways we're going to characterize that. And the other one is a component called phase. And so what phase talks about or characterizes is the difference, the offset between those two waves. And you'll hear this referred to as the current either leads or lags the voltage separated by theta. And so we'll talk more about that in a little bit. And here we also define omega as the angular frequency, or 2 pi f. So just as we return to the concept of Ohm's law and kind of apply that to EIS generically, let's return to Butler-Volmer equation. Let's talk about linearity. We'll talk about the importance of linearity. The Butler-Volmer equation really is used to determine how electrokinetics or how fast reactions happen. And so it defines this relationship of current, here I, to potential or over potential represented by eta. Now, when the over potential is small, we can expand this and we can ignore some larger terms through Taylor expansion series, and it's going to simplify and reduce. And the importance here is that when the over potential is small, that means that current varies linear with potential. And so we can see this shown on the graph over here on the right in the range right around the open circuit voltage. When I apply a small voltage, I'm going to get a small current back, and those are going to have a linear relationship. If I drove it with a very large voltage, you can see the relationship would become nonlinear. So what's the significance of this? It tells me that for a small voltage, whether it be an AC or DC small voltage, I can separate electrokinetics from that. However, if I'm applying just a small voltage in a DC experiment, I would not be able to get information about the mass transport. That information is held at large potentials for a DC experiment. But EIS can study a wide frequency range, and by doing that, I can capture information at the high frequency on electrokinetics, and I can capture information on low frequency diffusion or mass transport region, both in that experiment, both by applying a small stimulus. So now let's cover some of the criteria for valid electrochemical impedance spectroscopy measurements. We need systems to be linear, we need systems to be stable, and we need systems to be causal. So let's talk a little bit about what each one of those mean. First, we talk about linearity, and so if I look at again, we bring over the generic, the AC version of Ohm's law over here that says Z impedance now is the ratio of current to voltage. And if I think about this, if a system is linear, then the signal level of A would give a response B, defined by the relationship of impedance. But if the system's linear and I double the signal in, that means it's going to double the response out. Therefore, the impedance level measured and calculated does not change. Nor does it influence by which one, potential or current, is the signal and which one, the potential or the current, is the response. The next section is, the next key criteria is stability. And when we think about this, we think about how long low frequency measurements can take. Example we have here is 1 millihertz. 1 millihertz would be 1,000 seconds, and 1,000 seconds represents almost 20 minutes. And so that means to data capture just 1 millihertz on a single cycle, so an integration period of 1, it would take 20 minutes to take that singular point. So if the system is drifting during the course of the experiment, low frequency experiments would not be valid. Low frequency data would not be valid. So you can see then if we also cover causalities, just simply being that the response out is due specifically for your signal in, then we can go back and we can look at if a system's linear, if a system's stable, and if it's causal. That means that my EIS measurement is valid, but also it means that you can characterize it as being non-destructive because I've not changed the response by applying this EIS step. So why is frequency important? And we talked earlier about frequency is the tool in my toolbox that's going to allow me to apply a small signal and probe both high frequency or fast electrokinetics and low frequency or slow processes such as diffusion. But frequency does another thing for me as well, and that's going to lay the framework by which I do my data analysis. And that is because there are electrical components that have defined relationships between impedance and their value. And so when you look at this, the first one we'll cover, the most simple one mathematically, is the resistor. the impedance of a resistor simply is the value of that resistor. So now let's discuss the impedance of a capacitor. This equation does have a frequency component. Remember, we defined omega as 2 pi f. And so what this tells me is that the impedance of a given capacitor is very high when we are at low frequency and very low when we are at high frequency. The next component being an inductor. So an inductor also has a frequency dependence on its impedance, but that is a direct relationship, meaning that when we have at a high frequency, the impedance of the inductor is high, and at a low frequency, the impedance of the inductor is low. So over the next 4 slides, I'm going to take each one of these common components used in electrochemical equivalent circuit analysis, and I'm going to delve into examples of where you would see them in different types of electrochemical cells, representing different physical or chemical processes. And so the first example, the first one we're going to cover is going to be the resistance or a resistor. So when we think about where would I see resistance in an electrochemical cell, we could see that as solution resistance, which is the resistance between the working electrode and reference electrode, as we see kind of pictured here. Also the equivalent series resistance or the charge transfer resistance. So these are resistive values, and these are the things that are going to be modeled by resistors in our electrochemical models, and the models of our electrochemical circuit. So let's consider then, and think about the equation, and let's look at the value of a 1 kilo ohm resistor, and think about what its impedance looks like and how its impedance acts as we change the frequency during the experiment. And since there's no frequency dependence on the impedance of a resistor, even though I am sweeping the frequency, the impedance of that resistor does not change. And so we'll say the magnitude is going to be equal to the resistance value, and the theta that we talked about would be 0, meaning the current and voltage are in phase with each other. So the next circuit element we'll talk about is capacitance, or quick introduction to constant phase element. So what are some physical or chemical processes that occur in our cell that are traditionally modeled by a capacitor? Well, the first one that comes to mind is the electrochemical double layer. Remember, the electrochemical double layer is the state that exists because there is a charged electrode in a ionic electrolyte. A capacitor is formed because of the dielectric of solvation, or the water that's solvating the salt of the electrolyte dissociates the electrolyte, and those two charges cannot combine because those ions stay solvated. So let's consider what the impedance of the capacitor looks like as I change the frequency in the course of the experiment. Over here on the right, I've got I've copied in the equation for the relationship between capacitance and frequency on its impedance. And this tells me that at high frequency, the impedance is very, very low for this capacitor. And as the frequency gets lower and lower, the impedance becomes higher and higher. And so we could draw this on a plot that's going to give me a slope of a -1 line. The theta is going to be represented as 90 degrees, and that's going to be caused that the current and voltage then are out of phase. So this describes the magnitude, and then we see the description of the phase being out of phase by 90 degrees. I'm also going to introduce a concept here called constant phase element, because you'll see this often in the literature used as a replacement for the capacitor to model imperfect or leaky capacitors. And this will always give you a better fit of data, but simply because there are 2 degrees of freedom, or there's a single element that's fit with 2 different parameters. Since those two parameters are able to be adjusted, you're going to have a better fit using a constant phase element. So the next equivalent circuit element that we're going to discuss is going to be the inductance, or an inductor. Examples in electrochemical cells are adsorption processes, batteries, but also there's an example of instrument artifacts being of cell cables. So what is an inductor? An inductor is going to happen when you have a magnetic field created by current flowing in a loop. So a prime example of when you would see this in an electrochemical cell may be a battery, such as a form factor of like an 18650 lithium ion cell. These are generated by creating the most amount of material, energy density, in the smallest amount of package, and so they do this by then rolling up the current collector, and this current collector then has current flowing in a loop, thus creating this magnetic field that gets picked up by the voltage and sensed by the voltage leads, and is seen by an inductance. It's seen as an inductance. But if we think about how a potentiostat works, and we said that the current for the potentiostat is being sourced through the control amplifier that goes into the counter electrode, and it's being measured through the cell, then at the working electrode lead, back into the ID converter, we have current flowing in a loop there as well. So depending on the currents and depending on the frequency, you may see an instrument artifact which is seen as inductance at high frequency of low impedance samples. The current and voltage here are out of phase as well, just the opposite 90 degrees sign, and you still have that linear relationship and with frequency, and the slope of that line would be +1. So next thing we'll talk about is diffusion, and this is a little bit more difficult to describe with simple passive electrical components, because there's really not one that describes a diffusion phenomenon. So if we take that picture where we showed the electrochemical double layer previously, and let's keep walking out and expand that further, you're going to see the diffuse layer. And so in Nernstian experiments or Nernstian cases, such as electrochemical sensors, the potentiostat is poised the electrode to cause the electrochemical reaction to happen as soon as the ion gets to the electrode interface. However, that means current is waiting to flow until that ion can diffuse from solution and reach that electrode interface, the electrode-electrolyte interface. And once that happens, then the reaction happens. So that means I'm waiting for that ion to diffuse to my electrode, and since I'm waiting for that, it is a rate limiting step, and it's really the thing that's being sensed and defines how fast the reaction happens. These are slower, so generally we're going to pick this up at the low frequencies. So as an electrochemist, I'm going to study electrochemical cells. I'm not going to study simple electronic components. And so let's take what we have learned about resistors and capacitors and inductors and diffusion, and let's start using them to start building up some theory behind my electrochemical cell and describe how these experiments are done and how the data is analyzed. So if we think about it over here, I have the Randall cell, and the Randall cell is simply a resistor that's in series with an RC, or resistor capacitor network that were in parallel. And so this first resistor in series is commonly referred to, or commonly is used to characterize the solution resistance or the equivalent series resistance. Next, the resistor that's in parallel with the capacitor is used to quantify or to kind of mimic the charge transfer resistance, or the resistance to the Faraday reaction. That capacitor there then is the double layer, represents the double layer of my electrode-electrolyte interface. And so you can see why the Randall cell then is the building block for a lot of more complicated models, is the fact that virtually every electrochemical cell is going to have some form of solution resistance. It's going to have some charge transfer resistance, and it's going to have some double layer established. But let's look at the impact of frequency we're going to have here as well. The electrons are trying to flow through this circuit. And so which way is it going to go? Where am I going to see the different types of information? Well, at high frequency, what's going to happen is electrons are going to flow through that solution resistance, and it's going to get to that branch of the parallel circuit. At that point in time, I can go up through the other resistor, or I can go down through the capacitor. And how does the electron decide which way it's going to go? It makes that decision based on what frequency he is at. So when I get to that branch, I can go at high frequency, the impedance of that capacitor is low because of its inverse relationship. Therefore, that acts like a short, and the electron goes straight from the resistor, straight through, just as if that capacitor is not there. And so I only see, or the response is back, quantifies the value of that series resistance. As I step the frequency lower and lower, the impedance of that capacitor changes. And in the extreme example of very low frequency, now the capacitor's impedance is very high. And so what that means is my electron now, he still flows through that series resistance in front, but when it gets to the parallel network, it's forced up towards the, its path of least resistance is up through this second resistor. So at that point in time, the entire resistance, or at that point in time, the entire impedance measured is the combination of those two resistors because they're acting like resistors in series. What this does is gives me more information about the cell. And so it also gives me a way to identify what value, or assign a starting value for my solution resistance because of the high frequency. And then at low frequency, I now know my solution resistance, so I can solve for my charge transfer resistance. And then we use mathematical programs to approximate through and fit through to find values for that capacitor. These data are plotted in two different ways. They can either be Bode or Bode plots. Here on the left, the axes that you'll see here is the x-axis is the log of frequency, and the y1 axis is shown as the log of z, or the log of impedance value. You often see this graphed with the phase as a y2 axis, or on a separate graph. Over here on the right is the equivalent data, and that's important to understand. It's the equivalent data shown in a different representation. So it's two different ways to look at the same data. And over here we'll see a z double prime versus z prime, or a z real versus z imaginary plot. And so when we look at this, you can see in this example, at the highest frequencies of 100 kilohertz, so I'm reading this right off the Bode plot, I can look over at the impedance value there, and I can see that I had approximately 10 ohms of impedance at the high frequency. So again, that is a first approximation of how much of solution resistance or how much equivalent series resistance we had. You can see I start picking up this -1 relationship, the slope of the line being -1 in the capacitive region, and then down at the low frequency, you can see that I've picked up a solution resistance plus charge transfer resistance, and you can see that that's approximately 100 ohms then would be the approximate charge transfer resistance. And you will see the same thing over here, the Nyquist plot, but I'm going to use the next graph to show you this. So now let's take some of these different electrical components and look to see what their representations would look like on the Bode plot. So the top left-hand corner, I have the Bode plot of a resistor. Since a resistor does not have a phase dependency, there's not going to be any imaginary impedance. So we expect that the resistor's Nyquist plot would be a single point. It would be on the real axes, the x-axis, and it's going to be representative of the value of R. If we look below that, we can see the relationship of a capacitor on the Nyquist plot. Here from increasing frequency, you can see the relationship would be a vertical line of a pure capacitor on the Nyquist plot. So let's take that resistor and capacitor and let's stick them together now, and I'm going to get the vertical line from the capacitor, but it's going to be offset by that value of resistance. And down here, we're going to take this relationship and build upon it further to see what this Nyquist plot looks like for a Randall cell. This popular Randall cell, then I'm going to have an R1, an R2, and a C. And you can see at the high frequency here, I'm only going to have R1. At low frequency, I'm going to have the combination of R1 plus R2. Therefore, the diameter of the semicircle being the value of R2. So again, let's take what we've learned and look at how data is typically modeled in a real cell. So here is a Nyquist plot that we acquired on a lithium-ion battery that was used for a BlackBerry cell phone. And so what we've done is taken this this response, and we have built an electrochemical circuit analysis or equivalent circuit shown over here on the right, and then we use different software to fit these different parameters. And we can see we have an inductance shown here by a value going below the x-axis over to a time constant, RC time constant, represented by one RC network into another RC network. These fits, mathematical operations are going to fit these. To build equivalent circuits, we can look in the literature for great reference guides, and we can also start from our physical and chemical processes and work out to electrochemical models. Here's another great example of a solar cell, and it demonstrates the ability to measure 5 different regimes. We're going to get a series resistance, we're going to get cathode kinetics, porous electrode transmission line, and to recombination and into diffusion limiting response. We get all this information in a single experiment, and I'm going to be able to separate out these currents and assign different current values back to different physical processes in the cell, and I can do that because of the frequency dependence of these. So I'll talk quickly about the bandwidth of a system. So when we talk about impedance measurements, these are made as high frequency as megahertz level of frequencies. And so when we think about something in megahertz, the system needs to be able to respond very quickly. So how can we determine how quickly the system is going to respond? Well, it's going to be a function of the potentiostat being used, the cell cable, and the cell being measured at all also. And so that's because the bandwidth could be limited by the ID converter. If you're in a low current range, that low current range has a high current measurement resistor value, and that high current measurement resistor goes with the capacitance on the board and the cell cable and builds an RC time constant, and so that could be limiting your bandwidth. The rise time of your control amplifier could be limiting the bandwidth. Your high impedance reference electrodes could be limiting the bandwidth. Any additional instrumentation that's required for these measurements may be limiting the bandwidth. And so what potentiostat manufacturers do then is we're going to characterize the potentiostat itself and design specific calibrations and corrections to kind of compensate for the fact that of the bandwidth of potentiostats in their cell. We can see that in this type of graph. If you take a 100 milliohm resistor, and I'm going to sweep the frequency on a 100 milliohm resistor. So we'll think back and we'll say the impedance of the resistor is going to be constant. It's going to be just the value of that resistance. And so here what we expect to see is 100 milliohms flat across the whole entire frequency spectrum. And in the red plot, I get pretty much that. And that's using a galvanostatic EIS with a high current potentiostat, not a booster, that's going to have faster bandwidth. What you see out of the blue plot then is the same cell tested with a EIS through an external booster. So potentiostats that require external boosters to boost the current level or signal level to make these measurements, you can see below, we'll say 2 kilohertz, we're able to measure that 100 milliohms. But as I go to higher and higher frequencies, you're going to see this impact of what we call roll-off, and you can see the signal, the impedance value rolls off and deviates from the expected value. So what are some points for us to consider here? The vast majority of literature, when you start reading about EIS experiments, they're going to be taking potentiostatic mode experiments, and they're going to be using 10 millivolts signal. 10 millivolts because it's seen as a small enough voltage to be in a linear region on most cells, and it's going to be a high enough voltage to try and generate enough current for us to measure on the on most cells as well. So it's that kind of in between value. But you can use best practices on your system to determine which mode of EIS I should apply. Because if we think about, when we talked about linearity, we showed the example of how you can double the signal, double the response, and we generically talked about things as signal and responses being the ratio of which would give you the impedance. But we did not really talk about whether it needed to be an applied potential or applied current. And that's because the impedance value calculated is going to be independent of mode. So you'll hear talk about, when we talk about the energy talk in the application series, we'll talk about the galvanostatic EIS, and we talk about corrosion and physical electrochemistry. We'll generally talk about potentiostatic EIS and the reasons why we use these different modes. And then stimulus level, we'll talk about this again here over the next slide, but it's going to talk about the idea that I want a large enough signal to generate enough response for me to be able to measure it cleanly. But I don't want such a large signal that I drive the system into a nonlinear region. And some advice that we have here is to, only add when we take the results and we start modeling the results, try and only add equivalent circuit pieces or equivalent circuit components to your model if they have explainable physical or chemical processes in your cell. Next thing, you really want to consider the capabilities of the instrument being used for the measurement, and the reason we want to do that is to make sure we're not looking at instrument artifacts such as the inductance from the cell cables or capacitance of the cell cables, or if we're just measuring the input impedance of the electrometers. So I promise you a little bit more advanced EIS discussion over the next two slides, and one is a technique called harmonic analysis. And it's really a useful tool to determine the appropriate signal levels that you can and should apply during EIS testing. And so again, if the signal's too high, my response is going to be nonlinear, and if the signal's too low, my response may be noise dominated. So how do I know? Over on the left-hand side, I have this kind of the same graph we showed in the Butler-Volmer slide to demonstrate linearity. Now I'm looking at a value that is further away from the open circuit value, and it's now in a non-linear relationship. And so this is data from a single sine frequency of 180 hertz with a large stimulus. And so I get a nice AC voltage being applied to the cell, and then I get a response, but it's not a uniform. It's no longer a sine wave of current. This indicates I'm in the nonlinear region. And so how would I know that? Well, if I oversampled the data and performed a FFT, fast Fourier transform on the data, what you would see from this nonlinear data is a peak in amplitude versus frequency graph, a peak at the applied frequency, 180 hertz. And then you would start to see harmonics, or every 180 hertz, 360, and then 540. You'll start seeing as we go with frequency, 2 times the frequency, 3 times the frequency, 4 times the frequency, 5 times the frequency. You'll start seeing these harmonics drive out. The presence of those harmonics in a harmonic analysis would tell you that the signal you've applied is too large because we're picking up this nonlinearity. What this would also do is between the harmonics, you see basically a noise floor. And so what we want to do is make sure that our response at the applied frequency is large enough above our noise floor that we can confidently say that we're measuring the response with high quality. And so this harmonic analysis is an advanced tool that's going to allow you to understand whether you're in the nonlinear region or not, or linear region. Most electrochemical impedance spectroscopy tests are desired to be ran in the linear region. There is a small subset of material studies that do benefit from some nonlinear analysis. Another one we talked about was stability of your system. We talked about, well, who wants to speed up our EIS plots? EIS testing can have very long duration, and so that's going to be driven by the lowest frequency you measure. It's going to be driven by your data point density, and then the impact is going to be driven by system stability. So really, I want to test EIS faster. So there's people who are trying to study low frequencies such as diffusion controlled processes, specifically like intercalation of batteries, and then also samples that are active. So these applications really benefit from the ability to speed up the total EIS duration time. And so there's a technique referred to as Multi-Sine EIS that really is going to use the principles of that harmonic analysis we just talked about to really mix together and apply many different frequencies on an AC wave as possible. Up to here on this graph over to the right, I'm showing the 31 different sine waves kind of added together and applied to your system simultaneously. So the ability to apply a very complex waveform to your system and then extract all that data back out at the different frequencies allows us to drastically decrease the total test time down, where now it's just kind of dominated by the single lowest frequency instead of successive points all the way up to that lowest frequency. So let's review some key concepts and summaries. So electrochemical processes occur at different rates. The conversion of time, so DC experiments like ramps and DC biases, when we convert those to the frequency domain and study things using AC waves for impedance spectroscopy, we can separate out these different electrochemical processes. In general, fast processes like electrokinetics are studied at high frequency, and slow processes like diffusion are studied at low frequency. And EIS can determine the total individual mechanisms contribution to the characteristics of the cell in a single experiment. And this is going to allow us to do a lot of different things like fault analysis or study state of charge of batteries and this kind of things like this. Well, thank you for your attention. This concludes today's conversation on electrochemical impedance spectroscopy EIS testing theory as a technique. Again, this partners with the other introduction chapters on electrochemical theory and potentiostat working theory, and all these provide the framework by which we'll discuss more in depth different applications. Thank you and have a good day.